So we're going to present a simple derivation of the formula for the coriolis and centrifugal accelerations. Let's consider a point right here, point B, on the, say, a rotating platform. And this point B is at rest, and it's a distance r away from the center. Now, the direction of the rotation is indicated here on the diagram. Notice that with the right-hand rule, this is actually an omega vector that's into the page. Now this point B is at rest. This might be like a seat on the merry-go-round. Because of the rotation of the merry-go-round platform, that seat is going to move a little bit. So a little bit later, the point B will have moved over to here. Now, that means it will have traveled through an angle d theta, and it'll still be a distance r away from the center. That d theta, of course, will be omega dt, a little bit of angular displacement, it's the angular velocity times time. So how much did that point B move? What's its displacement dr? Well, using the arc length formula, we could just say it's r d theta, which is r omega dt. So if we want to find the speed, how quickly that point B is moving, then it's just r omega. Now this is a result we've seen before in Physics 1. We want to try and write that as a vector velocity. This previous formula is just speed. And if we use our right-hand rule, remember our omega vector is into the page. If we do omega cross r with the right-hand rule, then you'll see we get the correct direction for the displacement. So we're going to write this then as a cross product, omega cross r. Clearly this has the correct magnitude of r omega, and it also has the correct direction, as you can verify using the right-hand rule. Omega cross r will give a displacement in this direction. Now that was for a point at rest in the rotating reference frame. If the point happened to be moving, then for its velocity, v being velocity and of course r being position, then say you throw a ball on the merry-go-round. So the ball would have some velocity measured relative to the platform, and its velocity measured relative to the ground would be a vector sum of how fast you're throwing it on the merry-go-round plus this extra term that we just derived for the motion of the point B. And so that's due to the rotation. So that's how to find the velocity on the ground of an object that's moving in the merry-go-round reference frame. Now we can write that in a slightly different way, because of course velocity is the rate of oops, what's that? That's going in the wrong spot. Velocity is the rate of change of position. So this will be the ddt of its position measured relative to the ground. So the g is the reference frame. This is the rate of change of position as measured on the platform, the rotating reference frame. And this result can actually be shown to be true in general. For any vector quantity, its rate of change of that vector measured on the ground, the inertial reference frame, is its rate of change as measured in the rotating reference frame plus omega cross whatever that vector quantity is. So this is for a general vector quantity u. Now it could be any vector quantity. Here we applied it to the position r. Let's apply that result again to the rate of change of velocity, which is the acceleration. So we're interested in the acceleration of an object as measured on the ground. So you're not in the rotating platform, you're on the ground. Now we know that's the rate of change of the velocity. Which velocity? Well, the one measured from the ground reference frame, and the rate of change done from the point of view of the ground reference frame. Now if we apply the result that we just, and this should be a vector, rate of change of vector velocity. If we apply the result that we just found, because we're going to relate it to rates of change as seen in the rotating reference frame. So the rate of change is measured on the ground is the rate of change is measured in the platform plus a term omega cross that vector quantity. Now we're not done yet because this is still the velocity measured with respect to the ground, and we want to ultimately have a relationship with all platform quantities on this side. So we want to relate the velocity as measured with respect to the ground back to the velocity measured with respect to the platform. So we're going to substitute this in two places down below, here and here. So when we do that, there's the first place. And then here is the second. Okay, so clearly we have some work to do. All right, well, now it should be emphasized this rate of change was with respect to the platform. So I should have a little p there somewhere. Okay, so the first term is going to be the rate of change of the velocity measured in the platform, and the rate of change is also done with respect to the platform, plus, here we've got a time derivative of omega cross our platform, and that time derivative, that rate of change is as seen in the platform, and then there's two terms here, omega cross v, and then here's a double cross product, omega cross r. Now, when we go to do this rate of change, ordinarily we'd have to use the product rule here, but because omega, we'll deal with the case where that's constant, this doesn't have a rate of change. So this middle term here just becomes, I'm going to rewrite it all. All right, I guess I'll rewrite it all. But first I'll note that this is just the acceleration measured on the platform. So as we said, omega is a constant. So we just end up taking the rate of change of position. But of course, okay, and these two terms are still unchanged. Now, this, of course, is just the velocity of the object as measured on the platform. And so we have omega cross v, we actually have two omega cross v terms. And so the acceleration of an object measured on the ground is its acceleration measured on the platform plus these two extra terms. Now, if we rearrange that and express it as we usually do and say, okay, so what acceleration do you measure for an object when you're on the platform? Well, there's like a real acceleration of an object on the ground, and then these two terms will come over to the other side. So this will be minus 2 omega cross v minus omega cross r. And by the right-hand rule, you can show that if you just reverse the order of the cross product, that gets rid of this minus sign. And you can show that doing omega cross r and then crossing that with omega, that's just going to be with the minus sign in the same direction as r, and it will have magnitude omega squared r. So we're just going to then recover the equations as we had written them earlier. So the acceleration that you see on a rotating platform is the real acceleration plus a coriolis acceleration when you're moving in the rotating frame, plus a centrifugal acceleration. So this is a brief derivation to show where these two terms come from.